talk about much of that today. Instead, I'm going to focus on what I think is probably my favorite pet project, which is looking at glacier-wide stick slip events. How these glacier-wide stick slip events on this glacier Antarctica initiate and how they progress once they start, and how a lot of the variability and slip behavior in this glacier stick slip event seems to depend on the stress state in the system. And so my goal right here is really just to show you all some of the interesting things that we can see in this glacier stick slip cycle, and hopefully inspire some interesting conversation about how these observations do or maybe don't relate to what happens on faults that host earthquakes. My slides are not advancing. That's mysterious. There we go. Okay. So glacier with a stick slip cycle. So the study area that I'm going to talk about is the Whillans Ice Stream. It's essentially a large glacier in the Antarctic ice sheet. So this is Antarctica. The South Pole is right about here, and north is in every direction. So that's confusing. But the map is a map of ice surface velocity from satellite observations. And these kind of like reddish yellow areas are parts of the ice sheet that move maybe like a meter a year, while the sort of blue purpley areas are parts of the ice sheet that move maybe like a meter a day. And so what you can see is that there's these sort of like dendritic arms of fast moving ice that reach up into the ice sheet. And they are draining ice out of the interior of the ice sheet out towards the ocean. And these fast moving drainages are called ice streams. And that's just a little bit of glaciology lingo, but an ice stream is essentially just a big glacier within an ice sheet. So the Whillans Ice Stream is just a big glacier that's within the Antarctic ice sheet. And then these really bright purple areas are actually floating ice, where there's no longer any resistance to sliding, and so the ice speeds up really fast. But so the stick slipping glacier that I'm going to talk about is Whillans Ice Stream, and it's down here, kind of close to the South Pole. Right. And it's kind of the downstream portion of the Whillans Ice Stream. And so over here on the right, we're looking at a satellite mosaic image of Whillans Ice Stream, the part of it that stick slips. And we'll see this map a bunch. So this is a region of the ice sheet where the ice flows generally from upper left to lower right at about a meter per day. And on one side of the flowing ice, there's a region of stagnant ice, and then there's a shear margin here. And then on the other side, there's the grounding line where the ice goes from sitting on the ground to floating on the ocean as an ice shelf. And then downstream, there's a kind of a combination of floating ice and grounded ice. And so this whole area is, it's about 100 kilometers from the shear margin to the grounding line. And essentially this whole area moves by stick slip, unlike most glaciers that we know of. And so what that means is if you go and you put a geodetic instrument, a GNSS station, sampling at a high enough rate on this glacier, and you look at how this glacier moves through time, you record something like this. So over the course of 3 days, the glacier moves about 3 meters downstream, but it does it in these sort of like fits and starts. So, what we see here is that for the most part, the ice is moving pretty slowly or not at all. And then once or twice every single day, it suddenly slides forward in these glacier slip events where the ice moves something like half a meter to a meter in about 20 minutes. And these glacial slip events, they happen pretty much every day. And so what's happening is the ice is essentially becoming delaminated from whatever's underneath, and this whole area is like suddenly sliding forward over about 20 minutes. And so we think that these events are dominated by sliding of the ice across its base, not by deformation of the ice. And so if we zoom in on one of these slip events recorded by a single GNSS station on the ice, recording every 30 seconds, this is what one of these glacial slip events looks like. There's basically no motion, and then we see a pretty sudden acceleration over a minute or two, followed by a few minutes of pretty fast motion, and then this kind of long tail as the ice slows down over the next 20 minutes or so. And so, like I said, pretty much the whole area moves during these slip events. And so if you integrate the slip over the area and you sort of estimate a seismic moment equivalent, they're equivalent to a magnitude 7 earthquake. That's kind of they're very substantial slip events. There's a lot of mass moving during each one. And moreover, there are, in some events, sometimes from some parts of the basal fault, so to speak, the fault at the bottom of the ice, there is seismic wave radiation from sort of certain parts of the fault during these slip events. And I'm not going to focus on that during this talk, but we can come back to it if people are interested because it's kind of cool. Okay, so I'm in this seminar about earthquake physics. And so why are we talking about this glacier in the seminar about earthquake physics? So I think that these glacial slip events are actually a pretty interesting comparison to tectonic earthquakes for a bunch of reasons. They happen pretty much every day, sometimes twice a day. So we can gather a whole bunch of observations in just a matter of weeks. The fault itself is a field scale. It's 100 kilometers across. It's not like we've shrunk it down and put it in our labs. We can look at it. And then because the glacier is about 1 kilometer thick or so. So it's not that thick, it's relatively thin. And the displacements are pretty large. It moves, tens of centimeters to a meter every time there's a slip event. And so that makes the different sort of parts of the slip event actually quite easy to see with just simple GNSS instruments. You don't have to do anything really sophisticated to see slip sort of move through space during one of these events. It's not a lab experiment. This is just like a glacier out there doing its thing. It has all of its natural heterogeneity. And it also has a range of slip speeds from slower, to faster, maybe not like full earthquake, but still pretty fast for a glacier. And it sort of switches between slow and fast in space and time in these really interesting ways that I will get into in a little bit. And finally, we know where the earthquakes are going to be, so we can strategically instrument it, which is really useful, potentially useful. Okay, so glacial slip events. So this is, the entire glacier suddenly sliding forward over about 20 minutes, and we can kind of watch the slip spread out in space and time, similar to what we can do in the lab. I should mention real quickly that the data I'm going to present is from several different field expeditions to Antarctica, some of which I participated in and some of which were before my time. But I just want to acknowledge that there are like dozens and dozens of people directly involved in collecting this data, not to mention the hundreds of people who are involved in supporting logistics in Antarctica to make this work possible. So this is all, just data collected from the field in Antarctica by geophysicists on snowmobiles and occasionally in airplanes, but usually not. Okay, so let's get into this glacial stick slip cycle in detail. This glacial fault has some important features in common with earthquake faults that I think make it a valuable analog to sort of compare and contrast. So just like we can do for faults, we can estimate coupling. And so this map on the left is showing this thing that I call geodetic coupling, which is the proportion of total motion at a GNSS site that has happened during the slip events versus in between. And so it's a little different from seismic coupling, but it's essentially showing how much of the total motion occurs during these sudden slip events at the GNSS sites shown by these dots here. And so the white and light blue areas are parts of the ice that are like pretty stuck between these slip events. And the dark blue, blackish areas are parts of the ice that tend to move quite a bit between the slip events. So there's a couple of, big stuck patches surrounded by ice that continuously moves between events. The other thing that, previous people sort of discovered about this glacial fault is that just like we can do for earthquakes, we can figure out where the slip events begin. We can find the epicenter, so to speak, of the slip events. So this work was done by Martin Pratt using broadband seismometers and looking at motion on broadband seismometers to back project where the slip events begin. And he found that there tends to be that all the slip events tend to sort of the like main shock part of it tends to start in one of two places, either this red star or this yellow star. And we're just going to sort of take that at face value for this talk. So, you know, thinking about this previous work, what this geodetic coupling field reveals is like a couple of stuck patches surrounded by some ice that continuously moves. And so that's, you know, it's not altogether that different from how we conceive of how fault zones look like this sort of schematic of a subduction zone fault where there's lock disparities and, you know, conditionally stable fault surrounding it that may or may not participate in the earthquake. And so, yeah, it's kind of a similar picture here. We have kind of asperities and then creeping in the fault slip sense regions, areas surrounding the asperity. And this central asperity, this big light blue spot, is a major player in the ice stream earthquake cycle. It is continuously loaded pretty much by ice flowing in from upstream. And then from downstream, it is also continuously loaded, but modulated by sort of tidal fluctuations in the stressing rate. Okay, so I'm going to start showing some of like my work, showing how these glacial slip events initiate. I don't know if you like the word initiation or nucleation. We're going to look at what happens to start this sudden slip onset in space and time. And to look at this, I'm going to show data from a data set, a geodetic data set, a GNSS data set of 75 of these glacial slip events recorded at 7 GNSS sites over about 2 months in 2014. Okay, but first, let's pause for a moment and review, you know, how do we think earthquakes start? So in the classical nucleation theory of earthquake initiation, we might expect that we have some fault. And somewhere on the fault, there's kind of a region of slow slip that starts and it slowly expands in the same location, slowly sort of maybe gathering speed, expands until it reaches a critical size where the slipping region starts to expand unstably and an earthquake is born and the rupture spreads across some region of the fault. This is kind of how classical earthquake nucleation theory predicts that earthquakes begin, with the nucleation process in about the same place as the eventual hypocenter, which we call self-nucleation. And you know, given conditions in the earth, we would predict this to be like, I think, a few meters, not very big, something that would be pretty hard to see from the surface, despite lots of trying. However, there's lots of mounting evidence that not all earthquakes start this way. For example, this really well-known foreshock earthquake foreshock sequence that preceded the magnitude 8.2 Akike earthquake, in which foreshocks migrated pretty far towards the eventual main shock hypocenter in the weeks preceding the main shock. So examples like this, and from the 2011 Tohoku earthquake in Japan suggest that you know, not all earthquakes seem to initiate by this like self-nucleation process where this precursory process and the hypocenter are in the same place. And at least maybe some start with a large scale migratory process. Instead, that might be easier to see. And so, you know, we might hypothesize a different kind of earthquake nucleation process, one where there's some slow slip, or maybe a foreshock that cascades into some more foreshocks, that whatever the process is, as it evolves, it actually moves across the fault instead of stays in the same place. And for whatever reason, triggers the main shock to start kind of far away from wherever that process began. And then the rupture spreads across the fault again. And so in this sort of model, the initial nucleation process and the hypocenter are in different parts of the fault, which we might call migratory nucleation, and is potentially there's a much larger area involved in the nucleation. So that might be good, because it might be easier to see if earthquakes actually do this, if faults actually do this in the real world. And so I've given you these two kind of like end member ways that earthquakes might initiate, with the precursory process and the hypocenter in the same place or in different places. It's not really clear how it works on earthquake producing faults, but we can figure out which way it works on this glacial fault and ask the question, well, does migratory nucleation, is that a thing that happens in the world? And so I'm going to try and answer that question first using my my data set of 7 GNSS sites that were recording the position of the surface of the ice once every 30 seconds for about a couple of months in 2014. And so these 7 GNSS sites, they recorded 75 glacier slip events, because remember, there's one every day, sometimes twice a day. And it turns out that almost all of the 75 glacier slip events have some kind of slow slip precursor before the slip event, the main shock part of the slip event, begins. And so what does that mean? What does that look like? So on the right, we're looking at GNSS data, so position data on the top, and then on the bottom, we've taken the displacement and differentiated it to be a velocity. And we have one sample every 30 seconds. So it's kind of coarsely sampled, unfortunately. And then the colors of the lines correspond to the different locations on the glacier on the left. And so what we can see is, like, sometime around 10:07, one of the sites suddenly accelerates, and then all the rest of them also accelerate within a couple of minutes. And that's showing us that the main shock part of the slip event has begun, and the rupture has spread across the entire glacial fault within just a couple of minutes. Something like 15 minutes before that happens, there is this transient, slower slip pulse that happens at the orange, red, and gray sites, sort of down here. And so, there's a precursory slow slip transient that happens about 15 minutes before the main shock part of this particular slip event begins. And it turns out that something like this, not this exact pattern, but something like this happens before almost all of the slip events that we record with our geodetic data. So now if we go back to this idea of migratory versus self-nucleation, can we tell in this data set whether the precursory slow slip and the hypocenter are in the same place, or if they're in different parts of the glacier? And so to do that, we use the GNSS data, looks kind of like this, and we ask, okay, where does the precursory slow slip happen? In this case, at the orange, red, and gray locations. And then which epicenter does the slip event actually start at? And to answer that question, we have 2 GNSS instruments installed pretty close to these epicenters. And so we look at where does the precursory slip happen, and then where does the main shock start, right? Like, where does this fast part of the earthquake actually show up first in our data? And if they're in the same place, that's evidence of self-nucleation, and if they're in different places, it's evidence of migratory nucleation. And so in this particular case, it's pretty clear that the earthquake begins at this blue GNSS site. But the precursor was, the precursor is down here, and the orange and the red and the gray, and the slip of it begins at the blue site. So this is an example of migratory nucleation, where the precursory process and the hypocenter are in different parts of the fault. And so if we go through and we look at all 75 ice stream earthquakes in this data set, and we ask that question, where's the precursor, where's the epicenter? We find that 61% of these earthquakes show evidence for migratory nucleation. 39% of them kind of just don't have good enough data for us to see one way or the other. And then none of them show evidence of self-nucleation. So there's actually no positive evidence for self-nucleation, meaning there's never like a slow slip event on the blue thing, and then the blue GNSS accelerates first into the main shock. We never see that. So on this particular glacial fault, it looks like migratory nucleation dominates. So on this glacial fault, which has, abundant slow slip precursors before these glacier-wide slip events, predominantly shows migratory style nucleation or initiation process. If migratory nucleation can happen pretty much every single time that there's a slip event here, it probably can happen on earthquake hosting faults as well. Okay, so then the other interesting thing about this migratory initiation process, it turns out that it happens a whole bunch of different ways. It's not always like these orange and red GNSS sites move first and then the earthquake starts with the blue one. There's a couple different sort of patterns in how it happens. And it actually turns out that both epicenter areas, right, like both the blue GNSS site and the orange GNSS site can both show, they can both participate in being part of the slow slip precursor, and then they can both also be the site where the main shock starts, right? So they can participate in the precursor process, or they can be the epicenter, and it can switch back and forth between subsequent slip events. So this means that, the loading seems to determine where the slip behavior at those locations each time in a different way. It's not just some like local material property that says, okay, this is where an earthquake begins. So, again, thinking back to fault zones, this would suggest that just because a fault region sometimes has a slow slip event doesn't mean that it also can't participate in a large earthquake. Okay, so lots of precursors on this glacial fault, and the initiation process for the slip event seems to be predominantly migratory, and where the earthquake starts can move around, and the same part of the fault can be part of the slow slip precursor, or the same place, or the place where the earthquake actually begins, the slip event begins. So,
Chris, sorry,
yes.
it's Chris. I just feel like I missed something, probably would be distracted by taking notes, because you said that it's almost always this migratory nucleation, but doesn't this top right plot show self-nucleation? What am I missing?
Yeah, so the earthquake itself, so yeah, it's a little bit hard to see, I think, but the orange curve here actually is the one that like accelerates to becomes like fast first.
Okay.
And then it kind of, spreads back across the fault here.
Okay.
Yeah, it's kind of hard to see. It's kind of marginal, I guess. But the other thing,
because it just doesn't migrate very far, basically. Is that the idea here?
I guess the idea is that, the blue one kind of like starts to move. I wonder, can I make this bigger? Oh, I can make it bigger. Okay. Yeah, so the blue one kind of starts to move, but it never really gets going that fast. And then the orange one actually like accelerates into the fast part of the slip event first.
I see, right, and that they're really far away. Okay, I see.
Yeah, and they're like 45 kilometers apart.
Gotcha. Okay, I see now. Thank you.
Yeah, I mean it's hard to see here. It's a good question. Okay. Any other questions so far? Okay. Okay. So we always have this kind of like migratory process that seems to start these glacial slip events. But you might, reasonably think, okay, well, these GNSS sites were really pretty far apart. Like, is there actually any evidence that this thing is like migrating across the glacier and not just sort of like moving in one place and then triggering the slip event to begin? And so to answer that question, does it really migrate? I'm going to look at a broadband seismic data set now. So we're going to kind of switch instrumentation. And on the left is two data from two instruments in the same place on the glacier. On the top is a broadband, or on the top is GNSS data. So again, displacement down in the downstream direction, showing, you know, a slip event happening. And then on the bottom is a broadband seismometer in the same place. And so what we see is when the slip event begins, there's this gigantic wiggle, this big old wiggle. And then as the slip event proceeds, it's not much happens on the broadband seismometer. And then in this particular event, maybe there's a little bit of precursory slow slip as well. And we see this kind of funny negative long period kind of seismic wiggle. And this data it's minimally processed. It's basically taken out of the seismometer and it's been downsampled. So in terms of like what this is in terms of units, kind of hard to say, but it's like a few minutes long kind of like negative excursion on this broadband seismometer that seems to correlate with the sort of slow slip precursory part of the slip event. And we do have a couple of examples of this like long period negative seismic precursor on the broadband seismometers, where if you high pass filter the same data, you see a whole bunch of basal ice quakes. So these are just like little earthquakes happening on the slip surface of the glacier. And so that's pretty good evidence that what we're looking at is actually related. This like negative excursion on the broadband seismometer is probably related to sliding at the bottom of the ice. And we have a couple of observations of this, although it doesn't happen every time. And so if you believe me that this funny little wiggle reflects sliding at the ice face and the seismometer's response to that sliding, we can use that to look at how the slow slip precursor spreads out across the glacier prior to the earthquake beginning. So basically, we're going to look at how this little wiggle before the big pulse of the main shock, how that little wiggle spreads out in space. Okay, and so we're going to look at this like minimally processed broadband seismic data from this set of seismometers that kind of spread up and down the glacier. And then this figure up on the right is going to show the seismic data from each of these seismometers. And so about 20 minutes before the slip event begins, there's not much happening on the broadband seismometers. And then about 15 minutes before it begins, we start to see something happening at this site out here, kind of by the red star. And then we have one of these big negative wiggles on the broadband seismometer that, you know, for a while, it's pretty much just in that one place. And then as time goes on, it starts to show up at neighboring seismometers. And then as time goes on, it shows up further downstream and further downstream again before triggering the main shock part of the earthquake to start down by the yellow star. And then once that happens, we have those giant wiggles that show that the main shock is happening. And the rupture then spreads out back across the whole glacier. And so essentially what this is showing is some kind of slow slip process that if we back up, it kind of starts out in the middle of the glacier, and over the course of 15 minutes, it kind of spreads out before triggering the earthquake to start down by the yellow star. And so this eventual epicenter, this yellow star, is more than 40 kilometers away from where the first little broadband seismic wiggle starts. So this is pretty good evidence that actually there is actually a migratory component of how the slow slip triggers these earthquakes to start, these glacial slip events to start. we were able to find 5 examples of this funny broadband migratory process in this broadband seismic data set. It's not very long, so we couldn't find many more just because there wasn't very many more in the data set. But this does seem to be that like sort of one of the failure, what do we say, the patterns by which the glacier slip event happens, where it kind of starts out in the middle and then migrates towards the yellow star to initiate the slip event.
Grace,
Yes.
Can you remind us if the broadband seismometers are sensitive to velocity, acceleration? What are they, even without the, without the magnitudes, what are they seeing?
Yeah, they're sensitive to velocity, and the truth is that they, I think, all had corners of 120 seconds, so 3 minutes. So they're not very sensitive to anything, longer period than 3 minutes. And yet we still see these patterns. So they have like some sensitivity to longer period stuff. But it is not really clear what this is, to be honest.
Thanks.
Mm-hmm. Yeah, or it's not really clear like what the signal is, which part of it the signal is recording. Like, is it because it's tilted? Is it because it's sliding? Could be lots of things. Yeah, but we see some migration. Okay, so far, I have shown you that there are lots of slow slip precursors in this stick slip cycle on a glacier. And the nucleation or initiation process tends to be migratory, meaning that probably migratory type initiation can happen on natural faults as well. The same part of the glacier can slip slow or fast, and it can like switch back and forth between subsequent events, depending on the loading. And then finally, the nucleation process apparently does really migrate. So I want to show you a couple more observations. Yeah, so the next thing to know about these glacial slip events, we're going to transition a little bit away from talking about how they initiate, start to talk a little bit more about sort of the whole process. So the next thing to know about these glacial slip events is that they're basically slip predictable. So if we look at, how far the ice moves during the 75 slip events in the data set, we see this nice approximately linear trend with how far the ice slips and how long it has been since the previous event. And we get this kind of like range of recurrence times, mostly because the slip events they're modulated, let's say, by the tides in the floating ice nearby. So it's not always like 12 hours, 12 hours, 12 hours. They vary in terms of recurrence time. And so this nice, linear trend suggests that the glacial stick slip cycle seems to be slip predictable, which means, if we consider a constant loading rate over time, a slip predictable system is one where the stress or the slip deficit that accumulates between each event drops back to some background level during each event. So effectively like resets the system to start reloading from the same place each time. And that apparently is what happens on the glacier, which is kind of interesting on its own, but it's also really useful because it means that even though we don't necessarily know the level of shear stress on the fault, we can have a relative sense of shear stress depending on how long it has been since the previous event. And so this suggests a loading curve for the lock disparity that looks something like this as a function of time. On the x-axis, that locked asperity in the middle of the glacier is loaded at an approximately constant rate by just like continuous flow of ice from upstream and downstream. But then, of course, the glacier is ice, and ice is quite good at relieving stress by simply deforming. And so after some time, plastic deformation starts to become important. And we think this happens at some pretty large fraction of a day, which explains why the ice doesn't slip twice as far at 24 hours as it does at 12. So then, slip predictable system, whether the event happens at 12 hours or 24 hours, the shear stress on that central asperity seems to go back to about the same place and then reaccumulate with time. So essentially what I'm trying to say is that we don't necessarily know the shear stress on the fault, but we can estimate in a relative sense whether it's higher or lower based on how long it has been since the previous slip event. And so there are some pretty interesting things that actually co-vary with recurrence time for the glacial stick slip cycle. The first one is the duration of this slow slip precursor thing. So in this example that I've been showing you, the slow slip precursor lasts about 15 minutes from when the like orange and red and gray sites start to move to when the main shock begins at the blue site. So it's about 15 minutes, but that can actually vary quite a lot from, a couple of minutes up to like a couple of hours. And it turns out that how long that slow slip precursor lasts actually varies inversely with how long it has been since the previous event. So it seems that when it's been 24 hours since the previous glacial slip event, if we see this little slow slip precursor down by the orange and the red sites, we know that it's only going to be like a couple minutes until the main shock starts in the at the red epicenter. On the other hand, if it's only been 8 hours, it might take a couple of hours for the slow slip precursor to actually trigger the main shock to start. So that's pretty interesting. And then, if you believe me that the loading time is proportional to the shear stress accumulated on the fault, that suggests that the nucleation, initiation of these earthquakes happens faster when the stresses are higher on the glacier, which is pretty cool. Maybe not surprising, but pretty cool. I don't have a good explanation for kind of the spread of these yet. Still kind of trying to think about that. Okay, so then, and then once the main shock part of the event begins and the rupture spreads out across the entire glacier, we can measure, let's see. We can measure, how far did the GNSS site move? What was the peak velocity that it showed? And then what was the peak acceleration that it showed at each of these sites across the glacier? And so each panel here is the total displacement at one of these sites for all 75 earthquakes, the peak velocity at each site for one of these earthquakes, and then the peak acceleration for each of these 7 locations. And so, the main thing to see here is just that, and I guess this is kind of hard to see, but the x-axis for all of these is hours since the previous slip event, so the recurrence time. So the x-axis is essentially our proxy for fault stress level through time. And what you can see is that at pretty much everywhere on the fault, on the glacial fault, when the stresses are higher, when the recurrence time has been longer, the glacier slides further, slides faster, and in general, the peak acceleration is higher as well. And so we can talk about this more, but I think what this is showing is that kind of as a stress level on the glacier, the shear stress on this sort of stuck asperity goes up with time. The system is kind of edging towards being more and more like an earthquake, right? It's getting faster and faster. The peak velocities and accelerations are going up simply because the stress level is higher on the asperity. And then there's some crazy spread in the peak acceleration at the sites down by the grounding line. That's pretty complicated. but I could explain if anyone is really interested. Yeah, so essentially, as the stress goes up with the number of hours, however long it has been since the previous event, the slip event is sort of like more and more earthquake-like. Okay, so that's actually kind of the last observation I wanted to share with you all. But so what I've shown you is that, on the glacier, which has this really easy to see stick slip cycle that we can record a whole bunch of times in just a few weeks, there's lots of slow slip precursors. They seem to be migratory. The same parts of the fault can sometimes be part of like the slow slip part of the slip event, and then in the very next event be part of the fast part of the earthquake. I showed you that the nucleation process really does seem to migrate, and the duration of this nucleation process, or the initiation, whatever you want to call it, seems to vary with recurrence, inversely with recurrence time, which is a proxy for stress on the fault. And then also the total slip, peak velocity, and acceleration also vary with recurrence time. And I forgot to mention actually rupture speed. I haven't done this work, but someone else has done this work where the rupture speed also goes up with recurrence time generally. And so, these three things that I've highlighted here really seem to emphasize that the stress state seems to be controlling the slip behavior, whether a particular part of the fault is moving faster or slower seems to depend a lot on the stress state and the loading. Yeah, so that's kind of the main observations I wanted to share. I do have some stuff about the microseismicity, but I think it's a little bit, it's kind of a different set of, it's very different from these observations. So maybe I'll just stop and we can chat about all of this.
Okay, thank you very much, Chris. We're super interesting talk. I'll invite everybody to unmute long enough to join me in thanking Grace for fabulous talk. Really super interesting. And yeah, we can break into a time of questioning. Yeah, one simple way to do it, if you're not familiar with Zoom, at the bottom of your screen, you have a reactions button, and you can raise your hand the way Adriano Gualandi has done. Thank you, Adriano. So please go ahead, Adriano.
Hi, Grace. Thank you. Really nice talk and great observations. I wanted to ask about the asperity that you said is basically at like more or less upper right center of the figure in the left.
Mm-hmm.
You showed it in a previous slide that there was the asperity. Where was the location? I was wondering if you have any topography observation, or is it related to some different topography or ice thickness?
Yeah, there are some topography observations from ice penetrating radar. And there does seem to be a little bit of a high in the topography in the middle of the region. I don't remember exactly where relative to the asperity, but it is, yeah, there's definitely a little bit of topography there. But the topography is, something like 100 meters shallower out here versus like 100 meters deeper over here, over 50 or 60 kilometers. So the topography is pretty minimal. It's pretty flat. It's not entirely flat, but it's pretty flat over much of the area.
So you said we have extensions that are of the order of 100 kilometers, and the difference in height is of the order of 100 meters. Do I understand correct?
A few hundred meters, yeah.
Okay.
Yeah, which might be enough to do something, might be enough to route water somewhere else or something. Probably is enough to do things like that, yeah.
Okay, thanks.
Mm-hmm.
We do want to encourage everyone to participate in the discussion, so please raise your hand. Matteo, if you're ready, you go first, please.
Thanks. Great talk, Grace. I was wondering if you see any variability of the events in terms of delay or something like that with the temperature, the surface temperature at the glacier. I'm thinking about if there's a layer of groundwater in between the base rock and the glacier, and the temperature then could affect these events in the summer or in the winter.
Yeah, that's a very good question. And it's a good insight that, yeah, the presence or absence of water in different places might be affecting the stick slip cycle. In Antarctica, in this part of Antarctica, the surface temperatures, the mean annual surface temperature is well below freezing. So there's never any surface melt input into the system. So there's no seasonal variability other than how the tides can be kind of seasonal and affect things. However, there are lots of subglacial lakes in this area. So these are bodies of water underneath the ice, between the ice and the till or the bedrock, that do fill and they drain every few years in this region. And there is work showing that when these subglacial lakes fill and then drain and the water kind of like moves around underneath the ice, that it does affect the stick slip cycle. Yeah, in interesting ways.
Okay. Thank you.